Welcome to lecture 11 on mathematical foundations of robotics. In this lecture, we'll give a few first examples of limits of sequences. The computation of the limit of a sequence is largely facilitated by a number of theorems. So we are going to now introduce the first theorem, which is the theorem on sign permanence. This theorem says that if the limit of a sequence is a positive number, then the elements of the sequence will get closer and closer to this positive number and will remain positive definitively. So we have this statement, first statement, which is valid for finite limits, is the following. If the limit of the sequence an for n that goes to infinity is equal to some real number L with L larger than 0, then an will become larger than 0 definitively. A visualization of this is very easy because we can assume that this is the positive limit, the real limit of the sequence, and we want to prove now that definitively all the elements of the sequence will be closer and closer to L, so they will remain larger than 0. There is also a second statement of the theorem which is valid in the case of infinite limit, and the statement is the following. If the limit of an for n that goes to infinity is equal to plus infinity, then an is going to be larger than 0 definitively. So it is pretty similar to the other statement, but this is valid now for a divergent sequence. So let's start with the first one and give a proof of the first one. So the proof is very easy, and it is based on the just the use of the definition of limit. So let's use the definition of limit. For example, with the epsilon equal to L divided by 2. So we know that it must be true that definitively we know that an must be in this interval L minus L divided by 2 and L plus L divided by 2, or which is just like saying L divided by 2 and 3/2 of L. We are not going actually to use this. This part is useless. Okay, this is useless. We are just going to use the first inequality, which implies that an will be larger than or equal of L divided by 2, but because L is larger than 0, we know that this is larger than 0, and this concludes just the proof. Okay, if we want to visualize this on the real line, clearly we're saying that definitively it must be true that the elements of the sequence will be within this interval. Okay, So we can definitely say that they will remain positive definitively. Okay, let's now pass to the other statement of the theorem, and let's give a proof of this other statement. Now, from again, we will be using the definition of a divergent sequence to plus infinity. We know that uh, for any possible large positive barrier that we give, there will be elements of the sequence that will exceed this barrier. For example, okay, for m equal to 2024, we can say that a n will be larger than or equal of 2024 definitively. But this implies that clearly a n will be larger than 0 definitively. And this will conclude the proof. Now, it is easy also to observe that just the way we prove the theorem on the sign permanence, there are infinitely many theorems that we can prove. For example, so we can say that there are infinitely many theorems similar to the previous one. For example, let's consider the following limit. Let's consider limit of an for n goes to infinity equal to square root of 3, which is approximately 1.7. Okay, then we can certainly say that definitively an will be between 1 and 2. In fact, if this is square root of 3, which is between 1 and 2, by a proper choice of epsilon, we know that we can identify an n0 such that after that n0 all the elements of the sequence will be within this interval. Okay, so the important thing is just selecting a proper epsilon, but certainly we can say that this is gonna be true definitively. So how can we prove this? Well, we can easily prove this by giving a specific type, a specific value of epsilon, because we know that it must be true that 1 is less than square root of 3 minus epsilon, and 2 will be larger than square root of 3 plus epsilon. So this is just concluding the proof. There is another important theorem which is somehow in the background of what we have said so far. Remember that in the last lecture we said that basically for given a sequence there are only 4 possible behaviors. Well, we must now specify a little more what that statement entails, and this is evident in this theorem. Okay, theorem on the uniqueness of the limit. So what this theorem says is that a sequence an has only one of the 4 possible behaviors. And remember that those behaviors were 1, where we have a real limit, 2 divergent to plus infinity, 3 divergent to minus infinity, and 4 no limit. Furthermore, we say that if it is of type 1, it cannot be of another type. The same holds for any other type. So what I'm saying is that we know from last lecture that given a sequence we have only 4 possible behaviors, 1, 2, 3, and 4. What we are saying with this theorem is that the type of behavior can only be one of these. It is not possible, for example, that a sequence falls in category 1 and 2 simultaneously. Okay? So, of course, we should prove now, to prove this theorem, well, we should prove the incompatibility of every pair that we can extract from all possible combination of the 4 behaviors, but because they are very similar, let's just prove two of them. Well, for example, let's start by proving that suppose that an tends to L1, or let's say an tends to L, so an is a convergent sequence, and we would like to prove that this behavior is incompatible with the fact that an will tend to plus infinity, so it is divergent to plus infinity. Okay, how can we prove this? So we're saying that if an, so this is basically the proof that we're giving. So if an tends to L, okay, well, by just the definition of the limit for epsilon, for example, equal to 1, okay, we know that an will be between L plus 1 and L minus 1, which is to say that given value L, we are now taking a distance. Okay, the width of the interval is going to be 1, so this will be just epsilon equal to 1 and epsilon equal to 1 on the other side, and we know that definitively, this is true definitively, all the elements of the sequence will belong to this interval. Okay, but so let's assume now by contradiction that it is also true that an will tend to plus infinity. So for every possible large positive barrier we give, we know that the elements of the sequence will exceed this barrier. Okay, that implies that, for example, if we pick m equal to L plus 2, which will be somewhere here, for example, m equal L plus 2, we would expect that an should be larger than L plus 2 definitively. But this, of course, is impossible, is not consistent with the first one. So we have a reductio ad absurdum. So we just proved that there is incompatibility between two different behaviors for the sequence. There is also another part of this theorem which is maybe just better to include in the statement. And the other part is that suppose that we have if the sequence is of type 1, so it is a convergent sequence to a real number, then is only well, then there is only one real number L such that an tend to L. So what we're saying is that if the sequence is convergent to a real number, there can only be one real number, which is the limit of the sequence. So let's prove this second part of the theorem. So let's assume by contradiction that we have that an tends to L1, but also that an tends to L2, with L1 different from L2, and we can assume that L1, for example, is less than L2 without loss of generality. Okay, so then that we can say that if an tends to L1, it must be true definitively that an will be less than L1 plus L2 divided by 2. So let's see this with let's visualize this thing. So let's say that this is L1, okay, and this is L2. We know that definitively the elements of the sequence will tend to accumulate close to L1, okay? So from one point on, certainly we can identify an epsilon, some epsilon, so this is the interval, and we know that the elements of the sequence will be within this interval, okay? But at the same time, and of course we can pick any possible epsilon. For example, we can pick an epsilon which is less than the middle point between L1 and L2, which is L1 plus L2 divided by 2. Okay? The same way we can say that if an tends to L2, it must be true that definitively an should belong to this interval with range epsilon. So we have the elements of the sequence that will stay within this interval. So we can say that an is larger than L1 plus L2 divided by 2. But clearly these are two inconsistent statements. Okay, so we have now a reductio ad absurdum again. So this absurdum is just a consequence of the fact that we are assuming that the same convergent sequence will converge to different limits. Okay, so let's pass now to another very important theorem which is very useful when calculating limits, which is the so-called squeeze theorem. Let an and bn be two sequences of real numbers. If we have that an is less than or equal to bn definitively, then we can say that we have two possible behavior. If an tends to plus infinity, then it must be that also bn tends to plus infinity. So if the sequence on the left is divergent to plus infinity, this is pushing the sequence to the right to plus infinity as well. On the other side, if bn is instead divergent to minus infinity, this is constraining the left sequence an to be also divergent to minus infinity. Okay, so let's give a proof of this theorem. Now, we know that an less than or equal to bn definitively, okay? Well, this is just like saying that there exists at least one natural number n0 such that for every number n larger than n0, it must be that an is less than or equal to bn, just like the same thing. So let's now consider this case 1 and case 2. Okay, let me start with the case 1. We're saying that if an tends to plus infinity, let's see what that implies. Well, that implies that for every m real number, as large at will, there exists at least one natural number n1, such that for every number n larger than n1, it must be that an is larger than or equal to m. So this is to say that for every possible large positive barrier m, we can always exceed that barrier m with the elements of the sequence. But that also implies that if n, for every n that is larger than the max of this set, n0 and n1, well, in this case, if n goes beyond both n0 and n1, well, that implies that all the two statements must be true. So it must be that bn will be larger than or equal to an, and we are now just using basically the first definition, okay, the first statement. But we can also use the second statement now, namely the fact that an is going to be larger than m, which in turn implies that bn is larger than or equal to m. But this is just like saying that bn goes to plus infinity. So we have proved the first part of the theorem. Well, the second part, as you can imagine, is absolutely analogous to this. We just need to basically translate in symbol, use the definition of a sequence which is divergent to minus infinity. Okay, so this theorem is very useful because that means that we can evaluate the limit of a sequence without actually using the definition itself, by just comparing with another sequence of which we know the behavior. Okay, by just comparing the terms by terms, term by term, the two sequences, we can infer, we can extract an information about the behavior of the sequence. The following theorem is one of the most used, the powerful theorem, which is called the policeman theorem, and it is basically a variation of the squeeze theorem with three sequences. So the statement of the theorem is the following. So let AN, BN, and CN be three sequences such that we have two conditions to satisfy. AN is less than or equal to BN, less than or equal to CN, and this must be true definitively. Second condition is that AN tends to a real limit L, and also Cn tends to a real limit, the same limit L. Then from these two we can say that Bn, which is the sequence in the middle, will also be convergent to the same limit L, the same real limit. So notice that we are saying that this also shows that Bn is of type 1. Clearly, we are also saying not only the fact that Bn tends to a real limit L implies that Bn will be exactly of the same type of An and Cn. Okay? Good. Let's now prove this theorem. Let's prove this theorem, which is very relevant, very important in what we will be using and what we will be doing later. So what we wish to show is the following. We would like to prove that Bn is convergent to L. So for every epsilon larger than 0, Bn should be between L minus epsilon and L plus epsilon definitively, right? Or if we want to visualize this, if this is L and this is L minus epsilon, L plus epsilon for any positive number epsilon, we would like to prove that definitively the sequence Bn will be within this interval. Okay, so let's use the first condition. The first condition says that, remember that Bn is definitively within, is always larger than or equal to An and less than or equal to Cn definitively. Okay, so that implies that there exists at least one n0 natural number such that for every n larger than or equal to n0, we have that Bn is to the right of An and to the left of Cn. This is the meaning of definitively. From the condition 2, and specifically from this part of condition 2, we can translate this in symbols, okay? The fact that An is convergent to L, this implies that there exists an Na natural number such that for every n larger than or equal to an A, well, we know that An will be between L minus epsilon and L plus epsilon. Again, using the second part of condition 2, namely the fact that Cn is a sequence that converges to the real limit L. Well, this is very similar. We can say that there exists an NC now, because we are referring now to the sequence C, such that for every n larger than or equal to NC, Cn will be between L minus epsilon and L plus epsilon. Therefore, if we pick the max of the set N0, Na, and Nc, okay, for every natural number n which is larger than or equal to this, to the max, that implies that all the previous three statements must be true, okay? So which implies that basically L minus epsilon is less than or equal a n, and we are now using basically this part, okay, of the second statement. Then we can also say that an will be less than or equal of bn less than or equal of cn, and we are now using this statement. But also we can say that Cn will be less than or equal L plus epsilon, and we are now once again using the third statement, but only this part of the statement. But this implies that Bn will be between L minus epsilon and L plus epsilon, which proves the theorem. It is also easy to see that similar, so basically just one consideration, there were parts of the theorem that were not used, okay? So for example, we didn't use this part of the second statement, or we didn't use this part of the third statement. Okay, so that was a little bit more information that we just needed. Okay, it is interesting to notice that there are similar theorems. Similar theorem can be proved, saying that an, if an tends to L plus, okay, so the sequence an will converge to a limit L from the right, okay, to L plus n, Cn tends to L plus. Well, this will imply that Bn also tends to L plus. Okay, so this is easy to prove. This is left as an exercise. Okay, let's now try to apply the theorem to an example. Let's consider the sequence an equal to n to the square, and we would like to evaluate this limit, okay, by just using the squeeze theorem, for example. We would like to prove that an is divergent to plus infinity. Let's see how we can prove this. So the proof is the following. I wish to prove, so what is the definition of a divergent sequence to plus infinity? That for every m real, there exists at least one natural number n0, such that for every natural number n larger than or equal of n to n0, well then basically the sequence, which is n to the square, will exceed that limit, will be larger than or equal to m. Okay, now if m is larger than 0, which seems to be a reasonable choice, right? Because we know that when we look at the sequence which is divergent to plus infinity, we'll tend to consider very positive barriers. So then, what is the n0 that can be useful to prove this statement? For example, if we say that n0 is equal to the square root of m, well then we have that clearly for every n which is larger than this n0 equal to the square root of m, clearly we can say that n to the square is larger than or equal to m, because for such an m, right, if we have that n is larger than or equal to the square root of m, we have an inequality with both positive numbers, we can just take the square, and then what we get is exactly what we were looking for, and this must be true definitively. So we have just proved the inequality. So in this case we have evaluated the limit by just using the definition. Let's take another example. Let's consider the an equal to 1 over n. So this sequence is defined for n larger than or equal to 1, and it is always positive, but we would like to prove that an will tend to 0 plus. Okay, let's attempt this proof. Let's prove this, which seems quite intuitive, right? But we need to prove this, and we will now resort once again to the definition. So we wish to prove that for every epsilon larger than 0, 1 over n will be strictly larger than 0. Remember, the left inequality has to be a strict inequality for having a 0 plus as a limit. And on the other side, of course, we need to have epsilon, okay, because it would be a 0 plus epsilon, just epsilon, okay? And this must be true definitively. Now, if we pick, so we need to find out if there is a way of making this inequality to be true definitively. Well, the first part of the inequality, of course, we don't need to make any check because we know that 1 over n is always larger than 0. So we only need to check the second part, the fact that 1 over n is less than or equal to epsilon. But clearly, if we pick n larger than or equal to 1 over epsilon, and remember that because epsilon is very small, 1 over epsilon can be very large, but anyway, we can always move to the next integer. Well, that implies, by just reverting this inequality, that 1 over n will be less than or equal to epsilon. So we have proved just this by just using the definition. Okay, another example of a sequence could be the following: an equal to minus 1 raised to the n. And we know that this sequence has no limit, because this will attain values minus 1, 1, minus 1, 1. So clearly this shows an oscillating behavior. This cannot have any limit, but let's prove this. So we want to say that this has no limit. We need to prove this, and we will prove this by just proving that it cannot be any behavior like 1, 2, or 3. Okay, let's suppose that, for example, if an tends to plus infinity. Let's assume that this sequence is divergent to plus infinity. Well, that would imply that an must be larger than 0 definitively. And I'm using just the sign permanence theorem now. But this is impossible because we know that an will attain -1 frequently. Infinitely many times it will take the value -1. So clearly we have an example of reductio ad absurdum. This cannot be true. It cannot be possible that an will diverge to plus infinity. Okay, let's now assume then that an tends to L larger than 0, is convergent to some positive real number. Well, that the same way we can say that an is larger than 0 definitively, okay, by the same theorem on sign permanence. So because an will be -1 frequently, this is another example of reductio ad absurdum. Reductio ad absurdum. Okay, so let's now see if what happens if an tends to 0. Well, that would imply that an should be between, for example, -1/2 and +1/2 definitively. But again, because an, for example, will take the value 1 frequently, this is another example of reductio ad absurdum. Of course, I could also consider the case that an is going to be equal to -1. Anyway, it will be outside this interval between -1/2 and +1/2. Okay, so let's consider now if an will tend to some L less than 0, so it's convergent to L less than 0. Well, that would imply that an will be less than 0 definitively, but again, because an will be equal to +1 frequently, this is also impossible. The last possibility that we have is that an will tend to -infinity, will diverge to -infinity. But that the same way, this must be true. An should be less than 0 definitively. And for the same reason, an will take +1 frequently, so this is another thing that cannot happen. So another reductio ad absurdum. Okay? So because no one of the previous statement can be true, we can conclude that the only possibility is 4, case 4. Only possible behavior is behavior 4, which basically has no limit. Okay, so let's move to another example. Let's consider this sequence, okay? So you see, so far we have just evaluated the limits based on the definition. Let's consider now the sequence an equal to 2 to the n, and we would like to prove that this sequence is divergent to +infinity. Let's try first by using the definition. So we want to prove this statement. So we would like to say that for every m real number, there exists at least one natural number, n0, such that for every n larger than or equal to n0, then we have that 2 to the n is larger than or equal to m. Okay, so for any possible large positive barrier m, we can always exceed this barrier. Okay, so clearly if we pick m less than 0, well, this is a child play, right? Because we know that 2 to the n, of course, is going to be larger than m. Okay, because 2 to the n is just a positive number. So this is true for every n. Let's see what happens instead if m is larger than 0. Okay, well, then we would like to prove that 2 to the n is larger than or equal to m. But this is only possible. Okay, so we can just extract the logarithm base 2 of both sides. So we get that n should be larger than or equal of the logarithm base 2 of m. So this seems to be possible, but there is a caveat in this thing. So this requires to prove that 2 to the n basically is a surjective function, which is not that easy. Okay, it's not that easy. So we have we are left with the doubt that maybe not everything in this proof is totally clear. So we can now have an alternative proof by using the squeeze theorem. Okay, so let's suppose that we can prove that 2 to the n is larger than or equal n. Okay, well, if we can do that, then we can use the squeeze theorem, because we know that basically this will tend to plus infinity, so we can then conclude that also this will tend to plus infinity, so it will divert to plus infinity. So the problem now is to prove this inequality. Okay, we will prove this inequality. Proof of the inequality by induction. Okay, so let's prove this inequality by induction. We know that we have two things that we need to prove. So the base case, well, the base case is the fact that for n equals 0, we should prove that 2 to the 0 is larger than or equal to 0. But of course, this is just like saying that 1 is larger than or equal to 0. So yes, this is proved. Okay, done. And then we need to prove the induction step. Okay, namely the fact that if 2 to the n is larger than or equal to n, then 2 to the n plus 1 is larger than or equal n plus 1. Okay, so this is what we need to prove. Okay, from 2 to the n larger than or equal to n, if we multiply by 2 on both sides, we have that 2 to the n times 2 is larger than or equal to n. But this is just like saying, let me go here, and we can rewrite the left-hand side of the inequality as 2 to the n plus 1, and we can write the right-hand side as n plus n. Okay? But again, 2 to the n plus 1 because n is larger than or equal to 1, we can certainly say that n plus n is larger than or equal n plus 1. So we finally conclude the proof.